Hello everyone. Now today we will start with chapter number 5 of our statics course. Chapter 5 of the Hibbler book, which is equilibrium of a rigid body. So up till now we have studied about forces uh, and their resultants, and moments and their resultants, and the overall combination of these two acting on a body. Today we will start with how we can have a body which is at equilibrium, which means that net sum of the forces and the moments equal to 0. Secondly, we will also we have talked about a rigid body. Rigid body is a very important condition for statics because generally speaking, uh, if you squeeze an object, especially a soft object, with force from both sides, ideally this body should be in equilibrium because the forces are cancelling each other out, but any real body starts to deform. But in our studies, in static studies, we need to consider that there is no deformation and the body remains rigid. So again, we will start with the conditions for rigid body equilibrium. So you can see that there are two major conditions that are in the name. That one, it should be a rigid body, and two, it should be in equilibrium. That means no deformation and no no unbalanced forces. Okay, I'm not going to write net force, which is equal to net moments, which is equal to 0. And we will also talk about free body diagrams. This obviously chapter will be distributed into 3 or 4 lectures. Today we will uh, talk about these two topics. This topic will be continued in the next lecture as well, but let's just start with the conditions for rigid body equilibrium. So in order to understand what rigid body equilibrium is, we can consider any random shape, this sort of object O, for example, which is experiencing, you can see, 4 different forces and 2 different moments. As we have studied, we can assume that this body can be assumed to be a point which has the same mass and no dimensions. So when you assume that this whole body is just one point mass, then all of the forces are acting on this mass. And then if the body is understood to be in equilibrium, then all of the forces combined must cancel each other out, and so the resultant force must be 0. Okay, so they could be in any direction. We have studied in chapter 3 how you can achieve equilibrium based on different forces. And similarly, when you talk about these moments, there are 2 moments here. These 2 moments must also cancel each other out, so the body is experiencing no moment as well. Another question you can ask is this: if there is a body, if there is a body and it has different molecules or atoms in it, these atoms are not stationary as well, and they are not moving at a constant velocity. They are constantly moving at different velocities. They are interacting with each other. They are applying different forces. Any internal force which is happening inside the body cancels out among all of the different particles. So for example, if one particle is moving in this direction, there must be another particle which is moving in exactly the opposite direction. So that means that the all of the internal forces are again net sum into 0. So we are only interested in the external forces which are being applied, since the body does not start moving automatically on its own. So we can assume that there are no unbalanced internal forces. Um, so again, if any particle starts moving in this direction spontaneously inside this body, there must be another particle in its vicinity which starts to move in the opposite direction, which is again a consequence of the Newton's third law. Newton's third law is, for you guys who don't remember, it is every action must have an equal and opposite reaction. So again, the condition for a rigid body equilibrium is, again, the body must be rigid, it must not deform. If there is a force applying here, the body must not just deform here or start to twist here or anything. The body must maintain its shape, original shape, and there must be no unbalanced forces or moments. In reality, all bodies deform. Like we have talked about this in the class, but if you have even steel or concrete, and if you observe that under a microscope, you can see that deforming for a very small amount of time. But since these objects are generally very rigid, we can assume that they are perfectly rigid, and this will not affect our calculations by a significant margin. But again, if you apply these calculations on, for example, a rubber ball, then you will have a significant variation on your result versus the actual forces and displacements you can measure. So, uh, obviously, as we have discussed in previous chapters as well, when we are talking about forces, moments, or equilibriums, we can talk about those forces in 2 dimensions or 3 dimensions. So, in 2 dimensions, it is very simple that, like for example, if you see this plane here, you can the first question you can ask is, the plane is supposed to be 3 dimensional. It can sort of look like this. This is a very poorly drawn wing. There is an engine under it, and generally there are 3 wheels, one here and two here. But if you cut this wheel in half, sorry, this airplane in half, you can see that the exact same amount of force, which is called T here, applied on one wheel, it is exactly the amount of force which is applied here, assuming that this airplane is symmetric and it has the equal amount of passengers here, and the weight is actually equally distributed. So when you can assume this, you can just take this half and put it in a 2 dimensional space. So now only the weight is acting downwards, and this tire is just acting upward with the force of 2D, because both of these are combined, applying the resultant force upwards. And the front wheel is the same, because we don't need to, this can be assumed as a point, so this is applying a force of R. This is written here as well. So when we are talking about bodies and equilibrium, and especially when we take the assumption of a rigid body, what we can do is we can just ignore the whole big shape of the body, because we are assuming that, again, that the body is not being deformed in any way. So we can just ignore uh, this whole shape of the body and just take the resultant on the center of gravity or wherever the forces are acting. So when we draw this, again, this body as just a point with different forces acting on it, it becomes a free body diagram. Free body diagram means that this body is now free of all of the constraints. For example, if you have a mug sitting on a table, you can just draw this as a point which has a CG of air. You can just draw it as a point where this weight is acting downwards and the table is applying a opposite reaction. So now you don't need to know that this cup is sitting on this table. You just need to know that this body has a mass, has applying a weight this downwards, and it is being provided a reaction force of this upwards. As long as these two forces are equal, this cup will stay on the table. So it is very important that you must show all of the forces and the couples on the body. Like you cannot just ignore a force which is acting on this body when you're drawing a free body diagram. This is a free body diagram. Okay, so that means that you must incorporate all of the forces which are being acted here. So now we will see um, a couple of examples, actually many more than a couple of examples. But so for example, if this beam is resting on a roller, now you know roller can um, cannot prevent movement in this horizontal direction, right? Rollers are designed to provide little to no friction uh, if we are trying to roll them. But what happens is, what happens if we are trying to put force on top of the roller? It doesn't move because theoretically it is a rigid body and it should not deform. Realistically, it depends on the material of the body, but if we are talking about a steel roller, then this assumption is mostly correct. So when we talk about a roller, we can just simply replace this roller with a force F which is acting on this beam. Which is written here as well. So one of the important things you must consider is what is a support. Support is any object which is restricting movement of a body. If we talk about this as a body, then this roller is a support, which means this roller is preventing the movement of this body across the y-axis. Okay, so if you talk about this as y, this is x, so roller can only restrict the movement across y-axis. It cannot stop the beam from moving in x-axis. So support is support prevents the translation of a body in a given direction. For example, if you can apply a pin here, or something, if you weld this beam to the ground, or if you just fix this beam to some wall, then your moments will also be restricted. You cannot move, you cannot rotate this beam in any direction. So now this support will also exert a couple moment on the body. You will see in later examples how these supports are created and how these supports are. So for example, you can see here that now if we install a pin in a beam, what does that pin generally do? You must have you can see your door. For example, if you look at your door and if you look at the hinge, so you look at the door, here's the door, and there are 2 or 3 hinges which connected to the wall. And now if you try and pull on this door on any axis, you try and pull it outwards, or you try and move it in this direction, or you try and, for example, push it out of the board. What happens? These hinges stop you from doing that. So if we look at in 2D, that means that you are restricting the movement in x and y axis, and obviously also on the z axis. But if we talk about but if we talk about this door, if you try and just swing this door, apply a moment, this hinge will not stop you from rotating this door, ideally, right? It will stop you from rotating in this direction, or maybe in so if we talk about, let's say we draw the x, y and z. So you are free to rotate in the z axis, but you cannot rotate in y or x axis. So you can see that this is also applying a, a reaction force or a stopping force in the x or y axis as well, right? So a door hinge is restricting movement in basically three translationary axes, right, and two rotationary axes as well. It is just allowing you to rotate in the z-axis. This is, I'm sure it is complicated, but you, as you practice different problems, you can see the pattern and you can understand this pattern. Let's for now just go back to this pin again, and as you can see, if you just install a pin to this beam, now this beam can only rotate here, right, which is the moment axis, but it cannot move here or move here. So now your reaction is x and y. In opposite to that, what if we install this beam in a wall? For example, um, you have different beams, you have different structures which are installed in the wall, which support your, for example, if you look above the door, there is a beam which holds it uh, away from the wall. So what that beam is installed in is one side of the wall and on the other side of the wall. And now you cannot rotate or move this beam in any way. So what it does is, if you look at it in two dimensions, it is stopping both in the translationary axis and also in the moment as well. So this will apply any if you apply any force on this, this will apply an equal and opposite reactionary force. If you try and pull this will stop you from pulling it. If you try and apply a moment, it will apply an opposite moment. If you try and push it down, it will apply a regular movement, up to a limit, of course. So what that brings us is, where that brings us is the common supports and how we can represent those uh, in terms of forces, right? So our objective was to define different bodies and different supports as a free body diagram. We want to remove the physically installed forces. Like for example, we want to replace this cable with a force, or we want to replace this link with again a force. So what happens is, if you look at this cable, for example, this beam tries to move in this direction. So now, what does this cable do? This cable applies an equal and opposite force. But what if we want to apply force in this direction? Can a cable apply force in opposite direction? Cable means any rope, any wire, any cable. Can a cable resist compression? Generally, the answer is no. So for example, cables have very large strength as far as if they are pulled apart. When you try and apply tension to them, but if you try and compress, or if you try and push two ends of a cable, it will just start to crumple up and it cannot apply any reaction force. So you can see that this is only written with a inward force vector. So that means that this cable can only apply force in this direction if the beam starts moving in this direction and it applies a force. This is commonly seen in suspension bridges. Suspension bridges, you can see that are designed like this. So they are designed with an objective that all of the cables are sort of pulling the weight of this bridge, and they are always in tension. If the bridge starts moving upwards, then these cables cannot apply any force on them. Secondly, we can talk about a weightless link. Now, interestingly, in a weightless link, what happens if you try and pull it in this direction? This weightless link will definitely apply a force in this direction, right? What if you apply a force in this direction then? Because this is a solid beam, it will also apply a force in the opposite direction. So you can see that This is shown with a force vector of negative as well as in positive direction. Wherever we want to pick negative or positive, right? If we say this is plus F, this is then minus F. Third example, what if you install the this is similar to the example we saw first off as well. What if you rest a beam, just what if you rest a beam on a roller? So this beam has some weight and this roller will provide the opposite force. But what if you try and pull this beam upwards? If there is no other support on this roller cannot stop you from detaching this beam upwards, right? So you can just pull this upwards and this roller cannot do anything. So that means this roller can only apply a force when you push this beam downwards. So this roller has only force application in this direction. You can see that this is exactly opposite of the cable. So when you apply a force there, this roller has a reaction in this direction. Um, what if you have another support, another sort of rail in which this roller can neither move here or here, but it can freely move in these directions. So now what happens is, if you try and pull it outwards, this applies a force in this direction because of this rail, and if you try and push it here, this roller applies a force in upward direction. But again, you can see if you apply a force here or here, this roller cannot do anything because it is a roller and it is designed to move freely. Um, I hope this is not too complicated. We will have a discussion session on this, but right now if you just look at these, for example, if you apply a force in this direction, this roller will provide a force in the opposite direction because it cannot move above here, and if you apply a force in this direction, sorry, if you apply a force in this direction, the roller is stopped in this support and it applies a force opposite to this, and if you try and pull this roller in this direction, this support stops this roller and you get a force in the opposite direction. But again, these forces are just on a single uh, single plane and single axis. Similarly, considering a rocker, if you push this rocker in this direction or in this direction or perpendicular, what happens is this rocker starts to uh, sort of oscillate. But what cannot happen is this rocker cannot go inside this support ideally. So the only force, the only direction where you can't move this rocker is inside. So the rocker is applying an equal force outside if you apply any force which causes the rocker to go inside the system. Similarly, lastly, if you have a beam which you are trying to which you are resting on a surface, now the only direction this beam cannot go is inside this support. So that means there is only one force which is acting in this direction. So these were all forces which were sort of forces which are acting. Lastly, you can see if there is a pin installed here and this is on a slider, so that means that you cannot just move this rocker in this direction. You can move this in this direction and you can also rotate this rocker. So that means that only force is applied if you're trying to move this rocker either into the rod or out of the rod. But now let's look at some of the cases where we have two forces on a single support. For example, last example we saw that there was a pin at the slider mechanism. What if there is no pin and it is a single body which is installed? Now, if you try and rotate this, it should not be able to rotate because this is going to be stopped here. Or if you try and rotate here, this will going to be stopped here. So now you can see in addition to this force, we are also adding the moment. Again, you can move this rod freely in this direction. So there is no force in this direction, but you cannot move it in this or this direction. Similarly, if you have a pin here, again we talked about this as an example. If you have a pin here, you are free to rotate this, but you cannot move this rod either in this direction or this direction. You cannot displace this rod from this support. This is different from a roller where you can move this rod in this direction but not just in here. Now you cannot move this rod in any direction, you can just simply rotate this. So now there are two unknowns. Any force which is applied will have a resultant x as well as resultant y. Here as well, any force, if you apply a force like this, now let me draw, if you apply a force for example like this, so now this force will have a certain moment which will be resisted by the support, as well as this component which will be resulted by this force as well. But since you can see that this force also has this component, this beam will start accelerating in this direction. Uh, One of the last example is a fixed support. Fixed support means that you can neither move it here or there, nor you can rotate this beam. So now whatever you try and do, this beam will resist. For example, if we talk about a force like this, so this force has a component in this direction, and because of this distance, it has a moment direction. So now this moment will be resisted by reaction force here. This force will be resisted by reaction force at y, and this force will be reacted by this force x. So now it will have three unknowns. So this concludes our basic supports acting on a body, and hopefully we will have a discussion where you can try and solve different cases. I'll see if I can provide you some of the examples, and you can just see if there is a support. For example, again, see door hinges. If there are three door hinges, then what are the supports acting? Where can the forces happen? So I will share uh, an image with you guys on LMS as well, and you can see how the system actually takes place. Okay, I'll see you inshallah, um, guys, in the interactive session. Please try and solve the examples. Hafiz.